How's it going, everyone? And welcome to the very last section of Chapter 4, in which I'm going to discuss redox reactions. And so, I have to give you a heads up. If you don't remember this from basic chemistry or from high school chemistry, it's because you didn't like them and you completely blocked them from your memory, which I don't blame you, but unfortunately, you have to remember them. And so, first thing about some definitions. Oxidation means the loss of electrons. Reduction means gain of electrons. And so these first two definitions are the first of many, many confusing things about this whole concept. And so normally when you hear the term reduce, your brain kind of says losing something. But you have to remember that electrons are negatively charged. And so whenever you gain a negatively charged particle, your charge is being reduced. And so that's why in this case, if you reduce, you're gaining electrons. If you oxidize, you're losing electrons, as backwards as your brain may seem or make it. And so, in order to make things even more complicated, this is one of those concepts that the guy who came up with this idea long, long ago decided just to mess with everybody in the future. And so, the reducing agent is the reactant that loses electrons and is oxidized. Again, seems backwards because I just told you the opposite a second ago. Whereas the oxidizing agent is the reactant that gains electrons and is reduced. So one more time, let me say this very slowly. Reduction is the gain of electrons. Oxidation is the loss of electrons. But the agents are what cause this thing to happen. And so the reducing agent is what causes the loss of electrons to occur. The oxidizing agent is the thing that causes these electrons to be gained. And so these agents, they must be reactants. And that's why I have them in a completely different color, italicized, bolded, and underlined. And so they must be reactants. And so you can think about this, that the agents, they are the ones that are causing this reaction to occur. But once the reaction has occurred, the agents are done. Their job is over. They have retired and stopped doing anything. And so the agents have to be reactants, and they must be the entire reactant. And so if you look at the example I have on the slide, Cl2 plus 2Br minus. The Cl2 and the Br minus are reactants. And the Cl minus and Br2 on the other side are the products. And so in this case, your Br minus is going from I'll even point them out. Br minus, you can tell, has a negative charge there. And so here we can call this a -1 charge on this bromine. But whenever you flip it to the other side, Br2, that's a neutral compound. That's a diatomic, has no charge. And so in these cases, both of those guys are completely neutral, or both of the bromines are completely neutral. And so we know that it went from a Br with a -1 to a Br with a 0 charge. And so if you kind of look at this, it lost its electron. And so here it is gaining a charge. So it's going from a negative charge to a positive charge, so it's being oxidized. Where on the other end, our Cl2 on this side is completely neutral. So it has two chlorines, but neither of those chlorines have a charge. On the other end, we have two chlorines, but now they have a negative charge. And so this charge, again, is going from a 0 to a -1, so the charge is being reduced. So again, makes a little bit sense whenever you talk about the charges and not the actual electrons themselves. And so Cl is going from a 0 to a -1. Please note, both of these concepts I just talked about, in which bromine is being oxidized and chlorine is being reduced, I'm talking about this element, talking about the atom. I'm not talking about Br minus being oxidized or reduced. I'm not talking about Cl2 being oxidized or reduced. I'm not talking about Cl minus or Br2 being oxidized or reduced. I am talking about bromine atom is being oxidized. Chlorine atom is being reduced. And so here you need to just pay special attention to the fact only atoms, only elements can be oxidized or reduced. And so here you're going to have your bromine become a Br0. You can have your Cl neutral become a Cl minus. And so it's actually the atoms or elements that are undergoing this charge or change of electrons. Whereas on the other end, agents. Agents have to be reactants, meaning it can't be either of these two, and it's going to be the entire reactant. And so once you realize that bromine in this instance is being oxidized, the reactant that contains that bromine, please note, entire reactant. So the reactant that contains the bromine, which is being oxidized, is going to be the reducing agent. In this case, because the chlorine was undergoing reduction, the entire Cl2 is going to be the oxidizing agent. And again, I fully agree with you. It is the most backwards things ever, but I didn't come up with the rule. You can't blame me. I'm just telling you, you need to understand it and see how it goes. I have plenty more examples to go, so just stick with me through the rest of the video. You'll be alright. So, when we talk about these oxidations, whenever we have something that is not a metal or non-metal, or in other words, an ionic complex, or if we don't have something that contains like oxygen, then we need to find some way that we can kind of transfer, figure out how these electrons are being transferred. And so chemists, me being one of them, I didn't come up with the rules, but I'm a chemist. We use these numbers that aren't really real. And so I have to remind you, all of this stuff is theoretical. And again, pardon my language, but it's a bunch of BS. But it's the only way that we can make our brains comprehend how these electrons are moving around. And so these oxidation numbers are only created from rules. And so there are some underlying reasons why we do these, but you have to remember they are not real. And so they look very similar, and in some cases they are the same exact like number and value as ionic charges, but ionic charges exist. You can take a sodium ion and put it into a machine, and it will say it has a +1 charge. But if you find a sodium ion, you want to know the oxidation number, there's no machine for that because oxidation numbers aren't really for real. They're just imaginary numbers with imaginary charges that we made up just so we can kind of follow these electrons. And so, I said there's rules. That means apparently you have to know these rules. Promise you, not too horrible. So, for atoms in their elemental form, and what I mean by that is sodium as a metal, O2, like oxygen that exists as a diatomic, needs to be in its diatomic form for this to work. Again, oxygen in its elemental form, chlorine, Cl2 in its elemental form, phosphorus as a P4 in its elemental form has an oxidation number of 0. And again, makes a little bit of sense because in sodium as an element, it doesn't have a charge, it doesn't do anything with its electrons, and so it's just kind of be like sitting there. For monoatomic ions, and again, monoatomic ions, the ions with common ionic charges that are never, ever, ever going to change, the oxidation number is going to be equal to its ionic charge. For sodium plus, it's going to have an oxidation number of 1 plus. For oxygen 2 minus, it's going to have an oxidation number of 2 minus. For aluminum 3 plus, it's going to have an oxidation number of 3 plus. And so the sum of your oxidation numbers in a neutral compound must equal 0. And so if we're talking about sodium chloride, sodium is a +1, chlorine is a -1, again, just by like their common ionic charges. So that means sodium will have an oxidation number of +1, chlorine will have an oxidation number of -1, +1, -1 cancel each other out equals 0. But if you have a polyatomic ion that has a charge, then the sum of the oxidation numbers needs to equal the ionic charge. And I have an example on the next slide to hopefully explain that a little bit better. So, let's talk about group 1 and group 2. Group 1 and group 2 have common ionic charges of +1 and +2. So therefore, the oxidation numbers are also going to be +1 and +2. Not too hard to gather. Hydrogen typically is going to be a +1 with all nonmetals. Very, very, very rarely does hydrogen mix with a metal. But in those cases, it would be a -1. But please note, I put in like big red letters at the end. That is very rare. You will most likely never see something like that happen. And if you do, it's going to be a little bit outside of the realm of general chemistry. Fluorine. Fluorine we'll talk about later on in like coming up chapters, but fluorine is the most electronegative atom. Because of that, it's never going to get rid of its electron, and it's always going to be a -1 like ion. Then oxygens, as I've stated like a couple times, it's always going to be a -2 unless it's in that weird, annoying peroxide situation. And so most of the time, again, oxygen is going to be a -2 unless you see it as like that O2 weirdness. One exception to that is if it's with fluorine. So you have to kind of think of fluorine here as the top dog. If something's attached to fluorine, fluorine automatically gets the negative charge. Everything else is just going to have to deal with it and make up for the difference. Most things in group 7 are going to have, again, which includes fluorine, but most things in group 7 are going to have a -1 charge unless they're attached to fluorine, in which case, again, they're going to have some other issues. So I couldn't fit this next rule on the same slide, but it kind of continues on with the rule 6. So if you have a covalent compound, and I put in parentheses just to be sure you're understanding me, meaning it's not ionic, not a metal, non-metal. But if you have a covalent compound that contains all non-metals, then the element closest to fluorine will grab the negative charge. Everything else has to be a positive charge in order to kind of cancel things out. So let's do a few examples, hopefully make a little bit more sense here. So if we look at something like NO, I do not have any, so know these rules, and again, know which kind of falls into these specific rules here. And so in NO, we don't know anything specific about nitrogen because I didn't tell you any rules about it. Nitrogen does have doesn't really have a common ionic charge with it associated, or most of the time, but we know oxygen. Oxygen is going to be a -2 every single time unless it's in a peroxide. And so because we know oxygen is going to be a -2, in order for NO, which doesn't have a charge, in order for it to stay neutral, we need to have the same positive charge as we do negative, and so your nitrogen has to be a +2. And so same deal with your SO2. Don't really know anything about sulfur. There's not one particular rule about sulfur, but again, oxygen, -2 in almost every single case. And so if you look at -2 on the oxygen, additional thing you have to kind of ask yourself is there's 2 of them. I guess not ask yourself, remind yourself of. There's 2 oxygens. And so in this case, both of those oxygens have an oxidation number of 2. And so because there's 2 of them, your sulfur has to cancel out both of those -2s in order to become a sulfur +4. Please note, these are not ionic charges. So it should kind of freak you out to give sulfur, which is a nonmetal, a positive charge. But again, this is a fake number. It doesn't really exist. It's just going to be used in order to kind of track the movement of these electrons. ICl2. And so in this case, you have iodine, which is a nonmetal. You have chlorine, which is a nonmetal. So looking at it from an ionic perspective, both of these should be -1. But unfortunately, that can't work out when we start talking about oxidation numbers. And so in this case, you have to kind of follow the rule I have up at the top of the slide here. And I tell you the element closest to fluorine is going to grab the negative charge. The others have to be stuck with a positive charge. And so here, chlorine is closer to fluorine on the periodic table. So chlorine gets to pick up the -1. And the other end here, that means poor iodine, which again, hates to even try to do this, but iodine is now stuck with a +2. Because here you have 2 of your chlorines, both of those chlorines have a -1, and so your iodine has to make up for both of those -1s by becoming a +2. ClF3, this doesn't exist, but if it did, then we would again have to kind of acknowledge the fact that fluorine is the top dog here. Fluorine gets to choose the -1, everybody else just has to kind of go along with it. And so in this case, your chlorine would actually end up being a +3 because there's 3 fluorines, each with a -1, so your chlorine has to make up with it. So one thing I do want to kind of draw your attention to at this point is in my ICl2, my chlorine was -1. In my ClF3, my chlorine is now a +3. And again, it should kind of hurt your head a little bit to kind of even have to see that, But I have to tell you right now, it's okay because it doesn't exist anyway. It's all make-believe. And so these oxidation numbers are not real. Well, they're real as far as your grade is concerned, but they're not real in terms of they do not have this real charge anywhere on these ions or these atoms or molecules or whatever. So, last one here. NO3, same thing. You should kind of start seeing a trend with this, but oxygen is going to have a -2. But one additional kind of twist to this product or problem is you are sitting at a negative charge overall. And so if you have a negative charge, the sum of your oxidation numbers needs to equal to the ionic charge. And so here, the sum of the oxidation numbers between oxygen and nitrogen need to come out to equal -1. And so if we have 3 of our oxygens, we're looking at a -6 oxidation state for all 3 of those oxygens. And so then you have to make sure that you have a +5, not a +6. You don't want to cancel out all of them, but just a +5. And so in this case, 5 plus -6 equals a -1 overall. So if that wasn't enough, let's do a few more practice. Why not? So I want you to determine the oxidation number of the red element in each of the following compounds. An H2PO4 with a negative charge. And so for this one, use the rules that I've given you to kind of narrow down what you actually need to solve for. And so we know that hydrogen is always going to be a +1. Oxygen is always going to be a -2, unless it's an peroxide. And then you have +1 and -2. In addition to that, we have an ionic charge on this. So we know that the overall sum of these oxidation numbers needs to be a -1. And so here, again, depending on if you're more math-oriented, you can set this up as a simple math problem. So we know that -1 equals 2 of our hydrogens with a +1 and 4 of our oxygens with a -2. And we need to make sure that this thing comes out again with a leftover -1. And so your 3 plus your -8 plus 5 will give you an overall charge of -1. Same deal with your SO3 with the 2-. Don't know anything about the sulfur right off the bat, but we do know that oxygen is going to have a -2. We also know with SO3 with a 2-, our overall charge is -2. So the sum of the oxidation numbers need to equal -2. Since we have 3 of our oxygens and 1 sulfur, we need to set it up arithmetically that 2 or your -2 equals 3 times your 3 times your oxygens -2s. Or if we put in a +4, we have again +4 and -6 to give us a -2 overall. And then last but not least, the lesser of the horrible ones here. Oxygen, still -2. Hopefully you're starting to understand at least oxygen. And so the overall charge in this neutral compound is 0. But again, you still have 2 nitrogens and you have 4 oxygens. And so this involves a little bit kind of tweak of your math, but still the same math. And so for this one, you know that we need to have 2 of our X's since we have 4 of our -2s in order to equal 0. Or nitrogen, each of the nitrogens need to have a +4 involved with them. So my suggestion is do a lot of these practices. Again, redox reactions, it's always the downfall because people just don't really want to try at it. But they're not as horrible. If you like puzzles, that's all these things are. So now that we know how to identify in order to assign these oxidation numbers, let's see what all of this points to at the end. Something like this. So, I want you to determine the charge of each of the atoms. And then from there, we can determine if these are going to be reduced, oxidized. We can tell you which ones are going to be the reducing agents. We can tell you which one is going to be the oxidizing agent. We can tell you everything about this reaction if we assign the oxidation numbers correctly. And so, starting with the very first one of aluminum. Aluminum solid is the way that it exists in nature. This is its elemental form. And so aluminum by itself is going to have an oxidation number of 0. And the next product here we have Fe2 and O3. And so please note, whenever I was talking about earlier, like oxygen's going to have 0 on it, I meant if it's by itself. But as soon as oxygen is not by itself, and as soon as iron is not by itself, it's going to pick up the oxidation numbers that I talked about in the previous slides. So following the rules from the previous examples, oxygen's still going to be a -2. Because we have 3 of our oxygens, we know that's going to be a -6. And so our iron must be a +3 in order for it to cancel everything out in order to end up with an overall charge of 0. On the other side of things, we have iron. And so our iron, solid, as it exists in nature, in its elemental form, is not going to have an oxidation number. It's going to have an oxidation number. It's not going to have an oxidation charge. And so here you're looking at an oxidation number of 0. Then again, oxygen, surprise, it's still -2. Our aluminum in this case, 3 of our -2s, that means our aluminum has to be a +3. So now looking at these oxidation numbers, now you can tell me where these electrons went. Which way did they go? How did they get transferred? And so if we look at our irons, we see that we go from a +3 to a 0. And going from +3 to the 0, your charge is being reduced. And so we know that iron, please note how I wrote this. I'm saying the element iron is being reduced. Not the Fe2O3, not the Fe solid. I'm not being specific here. I'm just saying that atom of iron inside that chemical reaction is being reduced. And on the other end, we know that aluminum is going from a 0 to a +3. And so here we know that our aluminum is going to be oxidized. Now the tricky part here. Once we know this, we need to go backwards and figure out what the agents are going to be. And so, in this Fe2O3, it contains our iron. We said that the iron is going from a +3 to a 0, so the iron is being reduced. So the reactant that contains the iron, the entire reactant that contains the thing being reduced, is going to be the oxidizing agent. While on the other end, the aluminum is being oxidized. So the reactant, the entire reactant that contains the element that is being oxidized, is the reducing agent. And again, I fully understand and I fully agree with you, that is one backwards way of thinking. But the way that I can try to make it a little bit more sense is the Fe2O3 is causing the aluminum to be oxidized by doing this stuff. The aluminum is causing the iron to be reduced by pulling these electrons in this order. So I know it sucks, and I'm really, really sorry for telling you guys you have to memorize this, but it's the only way to go about it. So identify what is being reduced, and the thing that is being reduced, the reactant it's sitting in, is going to be the oxidizing agent. But again, agents must be reactants. These two had no chance. These cannot be the options in your multiple choice question. And so again, if it's asking about agents, you can usually narrow it down to 2 because there's usually going to be 2 reactants. Agents must be reactants. They must be in the entire reactant. Aluminum just happened to be the entire reactant here. That's why it's being oxidized and the reducing agent. So, the last thing I have to talk about here is the number of different types of oxidation reduction reactions. And so we've kind of talked about a few of these already. And if you want more information about these, please check out my slides on Blackboard, because I just kind of give you a brief overview on this, the video, because this video is already becoming too long. And so, combination reactions always occur whenever you add 2 things together. And so if you, again, add your sodium plus your chlorine to get sodium chloride, that is a combination reaction. One of the huge requirements for this, though, is one of those reactants must be an element. And so in this case, it must be an element because, remember, elements in their free elemental form have an oxidation state of 0. As soon as it moves on and becomes a compound, then they pick up an oxidation state. Decomposition rules, on the other end, are breaking this stuff apart. And so if you have NaCl and you throw it into water and it becomes Na plus and Cl minus, you have just undergone a decomposition reaction. if they didn't have a charge associated with them already. Displacement reactions, we've already talked about one of these forms repeatedly, in double displacement reactions, in which they swap their partners. Single displacement reaction really occurs whenever you have something kind of just steal somebody's partner. And the last but not least, combustion reactions, when you have some type of fuel and you mix it with oxygen to produce CO2 and H2O. And so real quick overview. X plus Y gives you Z, or whatever letter you choose. In this case, when you have two elements and they form to make a compound, either ionic compound or a molecule. But please note, I'm talking about two elements. And they have to be elements because potassium as an element has 0. Chlorine, again, Cl2, still diatomic, so it's still in its elemental form, 0. But once they combine, they can't be 0 anymore. Or you can have an element in a bigger compound to give you an even bigger compound. But please notice, one of these needs to be an element because O2, Cl2 is elemental form 0. As soon as they join up and become non-elemental or in their molecule, they're not 0 anymore. Decomposition would be the other way around. If you have a molecule and you break it into its individual components. But please note, again, one of the products must be an element because one of these things needs to have an oxidation state of 0 in order for this to be classified specifically as a redox reaction. Double displacement, not going to talk about it too much because you've seen a lot of examples of this. Precipitin reactions, acid-base reactions, all kind of fall into this category. But single displacement. In single displacement, X, it's all alone. Y and Z, they have a partner. They're nice and happy. But then X is just a big jerk and kind of comes in and kicks Y out of the place and steals Z away. And so here you have X and Z joining up and poor Y is kicked to the curb all by himself. Why would this happen? How does this happen? You need to be very familiar with this table. So please note what I have over here in big blue letters. You don't need to memorize the table. We will give you this table on the exam or on the quiz, but you need to understand what the heck it means and what it stands for. And so the easiest way that I can kind of describe this is I call this my totem pole. And so anybody on the top, they are top brass. They can do whatever the heck they want to anybody below. If you're all the way down here at the bottom or in the middle somewhere, everybody above you can push you around, can kick you around, and you just have to kind of deal with it. You can't do anything to anybody on top of you. And so in these instances, lithium can displace potassium, barium, calcium, sodium. Lithium can displace all of these. But if you're poor cobalt, you have a few guys below you that you can pick on. You can pick on nickel and tin and lead and H2 and all that. But everybody above you, again, is kind of out of your grasp. You can't do anything to them. And then you have poor old copper, mercury, and silver and gold. These are the least reactive of the elements, which is a good thing because this is what a lot of, not mercury. Mercury would be too messy. But again, gold, silver, and copper, this is why most jewelry at the very beginning of time was made out of these. Because again, gold, silver, and copper, the only things they can really displace is each other. Which luckily you are not made of gold or copper or silver, so you don't really have to worry about it too much. But say that you had like a lithium ring, not only would you kind of like start displacing your fingers and your cells, it can also displace hydrogen out of water, so you're literally chewing through your finger. Be aware of this table. Just know anything on top can kick out anything on the bottom. Anything towards the bottom, you can't do anything to anybody on top. Last but not least, as I kind of stated, combustion reactions. And so carbon-based fuels are normally the ones you'll be seeing. And so again, something like a hydrocarbon or even something that is composed of carbon, hydrogen, and oxygen. If you mix this stuff with oxygen, every single time, there is no ifs, ands, or buts. If you mix a hydrocarbon with oxygen, you're always going to produce CO2 and H2O. Those are the only opportunities, only chance that you actually have going for you. And so any hydrocarbon plus oxygen gives you CO2 and H2O. I say these are the most common. There are other examples of like nitrogen and things like that, but check out your book for those ones. And so in in combustion reactions, carbon is always going to be oxidized. And we know that because in CH, this has to be negative because hydrogen already has the rule saying that hydrogens are always positive. So regardless of the numbers, X and Y can be any combination of numbers, but hydrogen always plus, meaning carbon always has to be negative. Also, oxygen in its elemental form, always 0. And so going on this side here, though, your carbon is now teamed up with an oxygen. Oxygens are always 2 minus. And so this means this carbon has to be plus because it's attached to something that is already minus. In this case, carbon had to be minus because it's attached to something that's plus. So it's always going to go from negative to plus. Oxygen, on the other hand, elemental 0. And water, negative 2. Every time. And so here, always going to go from 0 to negative 2. So carbon, always going to be oxidized. Oxygen, always going to be reduced. But when we talk about the agent side of things, your CH, your hydrocarbon, is going to be the reducing agent, and we have our oxygen is going to be the oxidizing agent. Now we get to the very last slide, and I explain where this damn name came from. So oxygen is the main reason why it's called the oxidizing agent. Oxygen always oxidizes all this other stuff. And now you may hear the term later on, like again, iron. Iron forms rust because oxygen oxidizes that rust into iron oxide. That's all I got for you for chapter 4. So hopefully this does you a little bit of good and more than just reading the book. If you have any questions, concerns, then please let me know in email and all that stuff. Until I get chapter 5 ready and posted, I'll talk to you later.